So now we are going to verify whether the given three Cartesian equations of a plane have a single solution. Okay, a single solution or a unique solution, or you can say they have only one value for each x, y, and z. Okay, so how can we do that? Well, first of all, you have to check whether the planes are parallel. Okay, so let me give you an example. Okay, so let's say this is what it is given. Okay, so definitely you can say n1 is given as 1 comma 1 comma 1, and n2 is given as 2 comma minus 3 comma 4, and n3 is given as 7 comma 9 comma 13. They are not parallel to each other. Okay, they are not parallel to each other. So first three inconsistent systems are cancelled. Definitely. Okay. Now you have to check whether it is intersecting like this A. Okay, in a A type, are they intersecting? Okay. But when you're doing this, okay, when you're doing this, since they are not parallel to each other, okay, you can use another idea to verify all these things. Okay, instead of trying to prove that n1 is equal to n2 plus n3, or phi 1 is equal to s phi 1 plus t phi, s phi 2 plus t phi 3, you can actually use a specific verification method, okay, such that n1 dot n2 into n3 equals not equals to 0. Okay, if these are not if this specific expression is not equals to 0, you can say that the planes, these three planes, okay, these three planes have a single solution. And if this expression is equal to 0, okay, well then you should go and prove these two, okay, whether they are intersecting like this or they are intersecting like this. Okay, that is next step. But here we have to prove whether they are intersecting at a unique point. That's the idea we have to cover here. So let's do that. Okay, instead of this, okay, instead of n1 dot n2 into n3, you can also say n2 dot n1 into n3. Okay, or you can prove whether n3 dot n1 into n2 not equals to 0. You can either prove from these three, you can either prove any one of them. Okay, you can prove any one of them, and then you can find the unique solution. Okay, so that's what we are going to do here. Okay, so first of all, let's look at the numbers. Okay, instead of doing n1, I'm going to use n2. Yeah, n2 dot n1 into n3. Okay, so n2 is given as 2 minus 3, 4. Well, let's keep that at a, let's keep that aside, and let's just find out the cross product of n1 and n3. n1 and n3 will give you the values I, j, k. This is the determinant. Okay, this is the determinant. Okay, so here we have 1, 1, 1, and 7, 9, 13. Okay. So the I component can be written as 13 minus 9, so that is 4, minus j into 13 minus 7, so 13 minus 7 is 6, so that is 6, plus k into 9 minus 7, 2, so 2k. So we have 4i minus 6j plus 2k. Okay, so this will give us n2 is given as 2 minus 3 is 4, and n1 cross n2 is given as 4 minus 6, 2. That is equal to 8 plus 18 plus 8. That is not equal to 0. Okay, therefore they have a unique solution. They do have a unique solution. Okay, so this is how you can say this specific set of planes, okay, these three planes have a unique solution. I'm not gonna go through how to solve this yet. Okay, I'm not gonna do that yet. Okay, let's do another example to understand this more thoroughly. Okay, so let's say there is something given like here also we can see, let's write out n1 first. N1 is 1, comma 1, comma 1. N2 is 2, comma minus 1, comma minus 1. N3 is given as 1, comma minus 3, comma 6. Okay. Yeah. Here you can clearly see they are not parallel to each other. So now you will go to the next step, which is to find out N2 is where N2 dot N1 cross N3 is not equal to 0. That's what you have to prove. So N2 is given as 2 minus 1 minus 1, and you have to find the N1 cross N3. N1 cross N3 is equal to determinant ijk 1 1 1, and then we have 1 minus 3 6. So that is equal to I into 1 into 6 is 6. 6 minus 3 is plus 3, so it is 9 minus j into 1 into 6 is 6. 6 minus 1 is 5, so 5 plus k into 1 into minus 3 minus 3 minus 3 minus 1 minus 4. Okay, so the answer is 9 minus 5j. Okay, 9 minus 5j minus 4k. So I will write it down here. 9 minus 5 minus 4. That is equal to 18 plus 5 plus 4. And that is also definitely not equal to 0. So they do have a unique solution. Okay, so they do have a unique solution. So the planes pi 1, pi 2, and pi 3 intersect at a specific unique solution. Okay, keep that in mind. Now we can go to type 3. I'm not solving yet. I'm not solving for the answers. Okay, I will teach you in the next video. Yeah, I will teach you in the next video. But now, okay, because they are system of equations, it's related to system of equations. That's not what we do here. Here we are trying to understand how planes work. Yeah. So maybe in the next video, I'll teach you how to solve things. But now we'll go to the final boss. Okay, the final boss. There are three equations represent the same plane. If you face something like this, you can clearly see the same equation is multiplied by 3 here, and here we have multiplied it by 7. Okay, that's what happened. So this means all three equations represent the same plane, but what they have done is they are multiplied by a scalar number. Okay, so you can clearly see this also has infinite number of solutions. This also has infinite number of solutions. You can give any, I mean, they are overlapping with each other. So this is a consistent system of equations. Okay, so keep that in mind. Right, keep that in mind. And this is the third and final form. Okay, so it has been a long road. Okay, we had inconsistent. Okay, we had inconsistent and consistent system of equations. Okay, so in inconsistent, we had mainly the first one parallel to each other. Okay, they are distinct and parallel to each other, or they were not distinct because pi 1 and pi 2 were the same equation and pi 3 was parallel to pi 2 or something. Okay, and then we had the H type and then we had the A type. Okay, and then we learned about the infinite solutions. They are the planes intersected at a single line. Okay, line. This is pi 1, pi 2, and pi 3. Okay, and then we found out how to check whether it has a unique solution rather than infinite number of solutions. We used n1 dot n2 cross n3 to find whether they have infinite solutions or not. Okay, if it is not equal to 0, they have one solution. If it is equal to 0, they have infinite number of solutions. Okay, and then finally we have come to the three same equation for the three planes. Okay, that's all. You have to learn about the three planes, the interaction of three planes in vector space.
Thanks for watching the 45th and final video in our vector series. If you found this explanation of unique solutions and equations of the same plane helpful, don't forget to like, share, and subscribe for more tutorials. Hit the bell icon to stay updated with our latest videos. Check out the full playlist to master vectors and follow us on Instagram. Thank you for being part of this series. It's been a pleasure teaching you. I'll see you in the next playlist. Until then, keep learning and stay curious. Bye bye.